Hello, my name is Sayantan. This is a work in collaboration with Carl Marshall, Derek Norozizarai, Zhao Dong, and Senchen Lee. We present a novel graphics primitive that uses a network of memory instead of connected layers of perceptrons. One of the primary advantages of using our technique is that it makes inferencing more efficient compared to traditional multilayer perceptrons. This paper shows a variety of application of our technique in the context of neural graphics pipeline, such as textures, sign distance fields, shading, and neural radiance fields. We note that our technique is very general and may extend easily to other applications in graphics and beyond. At a high level, our technique blurs the line between learning and memorization. We hope to spur more interesting discussion and ideas in this context and in the context of neural networks in general. Next, we introduce our technique, differentiable indirection. It is similar to pointer indirection, where we query a memory location that points to another memory location containing the final output. However, in our case, we learn the pointer values using gradient descent. Both the pointers and the outputs are stored on a multidimensional regular grid. Since the array cells are discrete, we linearly interpolate the neighboring cells to enable continuous output and backpropagation. A key feature of such array is that they are fully differentiable. That is, we compute the gradient not only with respect to the content of the table, but also with respect to the array coordinates. The latter enables learning of the pointer values as stored in the first array. We call the first array primary, as shown in orange, and the second array as cascaded, highlighted in blue. We use a combination of primary and cascaded in a variety of configurations to enable various applications. To better understand our technique, we highlight one simple application of differentiable indirection in the context of PBR shading. Specular BRDF lobes are often modeled using isotropic GGX, as described by the following equation. The equation has two scalar inputs, alpha and h, and outputs a single channel nonlinear HDR value. Here we use differentiable indirection to approximate the function. The two inputs to the function are used as the coordinates to sample the primary array, a 2D array with two channels. The primary array then returns the 2D coordinates to sample the cascaded array, which contains the final output. In this slide, we visualize the learned representation of isotropic GGX as stored in the primary and the cascaded array. Here, we compared the analytic and approximate output on a scene rendered with a variety of sharp and diffuse specular lobes. The following plot shows the key takeaway of our approach. We compared the resource utilization for various alternative neural architectures for the same task. Note that our technique requires fewer compute flops and memory bandwidth compared to MLPs, and lesser parameter space compared to single-level lookup tables. Next, we show a variety of other applications of differentiable indirection. We start with our SDF representation. Our technique uses a 3D primary and a 3D cascaded array. We query the primary array with a spatial coordinate, and the representation learns a mapping from the spatial coordinates to binary density, either a plus or a -1. Here, positive and negative indicates exterior and interior of a geometry respectively. The output of the representation is used to construct a 3D mesh using marching cubes algorithm. The video compares the reference KD tree oracle on left with our technique and multi-resolution hash encoding. Notice the piano keys and the space between the two plates of the piano cover. The next application uses differentiable indirection for image compression. Here we use UV coordinates to query a 2D primary with 4 channels, while the cascaded is a 4D array storing the output RGB values. Our empirical observations show that increasing the dimensionality of the cascaded array improves the quality of the output at a given compression. Here we show the output of our technique at 6x compression. Next, we make a small modification to the compression-only network to also incorporate texture sampling based on pixel footprint. The network additionally uses a pixel footprint estimate to output an alias-free LOD-appropriate RGB output. We show its application in regular albedo textures and normal maps. Notice how seamlessly we transition from coarse LOD to fine LOD using our technique, while compressing the representation by 6x at the same time. Our technique produces slightly blurrier results at coarser LODs closer to the distant horizon. ASTC, on the other hand, produces much noisier results at comparable sample count. Next application shows the approximation of Disney BRDF using our approach. Similar to isotropic GGX, Disney BRDF models the appearance of a variety of complex materials. In this application, we split the primary and the cascaded into an offline encoder and a runtime decoder to improve efficiency. The offline encoder encodes the artist control parameters, which are often stored as regular textures, into another set of encoded textures. At runtime, these encoded textures are used by the decoder. Again, we compare our technique with the reference implementation in this slide. Next, we show an end-to-end combined texture sampling and Disney shading for two different scenes. We move to our final application in radiance field compression. Here, we use two independent networks to compress the density and the radiance field. Both networks are queried by a 3D spatial coordinate. One outputs a scalar density and the other a 12-channel latent vector. The latent vector is then combined with view directions using positional encoding to output a view-dependent RGB color. The video shows the comparison between reference uncompressed grid on the top left and multi-resolution hash encoding compressed grid on the bottom left. Thus, we conclude our video demonstration, and thank you for watching.